Hi, good morning on this snowy day. I hope you guys are all safe, but at least enjoying how pretty it is, and I'm sure hopefully doing some shoveling later if you live at home. So we're going to go ahead and continue with drawing Lewis structures for molecules. So a couple things to keep in mind. Remember that if we look at the columns in the periodic table, so like this is 4A, 5A, 6A, and 7A, we're going to have typical bond formation is going to do whatever it needs to get to 8. So with carbon there, you see that it's going to have 4 bonds. So up here in blue, I'll put the number of bonds. Now, we did talk about this at the end of class, so this is a review, but just to remind you. So those are the typical number of bonds that are going to form. And you can see this if you draw a Lewis structure, with hydrogen. So let me actually color code these for us. So I'm going to draw the hydrogens in red. They come in with 1 valence electron. So the first step in any of these is to draw the correct number of valence electrons for each atom. Because all you get to do is pair things up or redistribute the electrons, but you don't get to get rid of any electrons, okay? So now we're going to go ahead and make sure that everyone has a pair, because that's how electron comes. They come in 2s. And we're going to connect the carbon ones to each hydrogen. So instead of a dot, we now create a line, which is still an indicator of 2 electrons. It's just that they're now being shared between the carbon and the hydrogen. Okay, so similarly, nitrogen is going to have what we call a lone pair. I think your book sometimes calls it a free pair, but it's alone, meaning it's only attached to that one atom. Okay, and then it has these 3 unbonded electrons, and that is what's going to bond with the hydrogens. So when we look at compounds of carbon, nitrogen, fluorine, oxygen, and we look at how many hydrogens they bond to in nature, it looks just like this. Fluorine ends up having just 1 bond to hydrogen because it's got this 1 unpaired electron that needs a pair. So if we're to combine hydrogen with fluorine, we're going to see that it forms this 1 bond, and no other hydrogens are going to come along and bond with the fluorine because its octet is satisfied, and there just isn't any, really it comes down to energy motivations. There's really no energy motivation for any other hydrogen to bond to that fluorine, okay? But the way that we summarize that is by talking about the octet being satisfied. And obviously, like we mentioned before, the duet for hydrogen. Okay, so going back in and pairing up these electrons, this is what each of those elements would do in the presence of hydrogen, how they would bond with it. Okay, and this question down here, we already answered that up there. The column number correlates to the number of bonds by being whatever 8 minus the column number, if you want to think about it in a very formal definition. So for oxygen, for example, 8 minus 6, that's 2 bonds. Okay? Number of bonds. All right. So let's move along to talking about a little bit more complicated. We're just going to get a little bit more complicated. And by Wednesday, we're going to kind of get into the things that are more exceptions. And so they're complicated such that we can't really rely perfectly on all these rules. Okay, so we're going to start by drawing some of the diatomic elements. And you should know this from Chem 1. There's 7 diatomic elements, meaning that they come in pairs and when they're by themselves. Obviously, like if they're, oxygen and hydrogen, there's 1 oxygen, there's not 2. Or F and H, there's not 2 fluorines, there's not 2 hydrogens, there's just 1 of each. This is just when the element is by itself. So when it's just nitrogen, it's going to come as N2. Okay? So what we want to do here I don't know that I want to do every single, oh, it just says nitrogen, oxygen, and hydrogen, or fluorine rather. That's good. Okay, so we're going to draw the Lewis dot symbol for nitrogen. And even though these are the same elements, I'll go and color code the electrons just so you know. And we're going to do this for nitrogen, oxygen, and fluorine. And we're going to see, knowing that these elements are diatomic, meaning that they come in these pairs, how do they form bonds? Sorry, I said I was going to do those in red just to differentiate them. Okay, so let's look at fluorine first. When fluorine bonds, you remember that it has these 3 sets of lone pair electrons on each atom, okay? So 3 lone pairs, or another word we might use for that is non-bonding pairs. And then we have the 2 electrons that do not have a pair, and therefore the atom's octet isn't complete. So the way we're going to bond those is just share those 2 electrons. And now when we look at it, let me erase some of these. When we look at it, we can claim that bonding pair for both that fluorine as well as for that one in order to count up their octet, okay? To say, is the octet satisfied? We get to double count that bond. So just kind of checking, the fluorine on the left has 2, 4, 6, 8 electrons, so its octet is satisfied. And then on the right side, 2, 4, 6, 8 electrons. Okay, so that bond gets counted for each fluorine. All right, now moving on to the oxygen, there's 2 pairs of non-bonding electrons on each oxygen atom, but there's also those 2 individual electrons. And we don't go like this. We don't pair them up like that because number 1, that's not how they'll exist. They're going to be separated until they have to come together. And number 2, that still doesn't make their octet satisfied. They still only have 6 electrons, okay? So what'll happen is that we'll get a shared pair that doesn't satisfy the octet though, because right now, oxygen has 2, 4, 6, 7 electrons, so we can't be done. So what we're going to do is pair up the other set, and now when we look at it, the oxygen has 2, 4, 6, 8. Because they always come in pairs, you can start to think about it as a line or a dot. You could just count those as, because we know that those are equal to 2. We can say that we're looking for 4 pairs of electrons. So when you count them up, you can just say 1, 2, 3, 4. Because that's equivalent to 8 electrons. Okay, so whatever is easiest for you. All right, so what this means, I replaced that bond I just deleted. What that means is that when oxygen forms a molecule with itself, how it appears in nature, how we breathe it in, it has a double bond. So to kind of clean up this structure, we would draw that as a double bond just next to each other. And then you can either draw the electrons like on the sides, the way we've been doing, or what you'll start to see me doing is drawing them at an angle like this. And I'll explain why I do that eventually. But neither one is right or wrong. They both look fine. But we don't want to leave it like this because that just looks messy. So we do clean it up and put those double bonds all in the middle together. Okay? All right, now moving on to nitrogen, you can kind of see where we're going with this. In order to satisfy the octet, we're going to form 1, 2, 3 bonds. Okay, so let me redraw that structure and then I'll show you how the octet is satisfied. So the nitrogen's going to have a triple bond and then one non-bonding pair on each atom. So if I say for this nitrogen, is the octet satisfied, I count 1, 2, 3, 4 pairs, or 2 times 4 being 8 electrons. So 2, 4, 6, 8. So whichever way you want to count them, you either need to have 8 total electrons or 4 pairs. Okay, so that nitrogen's octet is satisfied. And then obviously the other one is identical, so it's going to have its octet satisfied. Just remember, when you're checking to make sure the octet is satisfied, that's when you get to double count those bonds. There's going to be another time on Wednesday where we talk about another technique, and we're going to split the bonds between the two atoms. That's not the same thing that we're doing right now. Right now, we're just checking to make sure that the octet is satisfied. Okay? All right. We've kind of already talked through that. Does this still match with what you said about the number of bonds an element will typically form? So let's go look at our list. Yep. Oxygen was supposed to have 2 bonds. Nitrogen was supposed to have 3. Fluorine was supposed to have 1. It's just that the bonds they formed were with each other. So if you look at this nitrogen compound, it has 3 bonds with 3 different atoms, hydrogen. But when we look at this one, the nitrogen has 3 bonds. It's just with another nitrogen. So it's 3 bonds as a triple bond rather than 3 bonds as 1, 2, 3 individual bonds. Okay. All right, moving right along. Looking at the Lewis structures for N2O2 and F2, circle which one you would expect to have the shortest bond and strongest. Okay, you can go ahead and Google these if you want. I have this formalized in a couple slides down. Oh, I guess it's in the end of the chapter. That's fine. We'll get to it in detail in a minute, or not in a minute, in Wednesday. But the thing that we want to connect here is that the more bonds there are, so like a triple bond versus a double bond versus a single bond, the more bonds there are, the shorter the bond is going to get and the stronger the bond is going to get. So N2 actually is going to have the shortest and strongest bond because there's 3 of them versus F2. That's going to be the longest and the weakest of this set. Okay? And we'll formalize that, like put it in the notes at the end of this chapter. Okay, moving on to something even more complicated. Now, we're going to have to tell you most of the time which atom is either in the middle or kind of how the structure looks in general. What I'll do sometimes is I'll give you what I call a skeleton structure. So I will put the elements like this and say, you know, the carbon's in the middle and then these 3 atoms surround it, or even start to draw the bonds in for you just to give you an idea of what the structure looks like. But you should still start by drawing each element with its correct valence electrons and don't rely on the bonds that I give you because you don't actually know if those are double or triple or single bonds. What I'm just telling you is kind of how each atom is bonded to each other. Now, when you get more and more familiar with this, you actually should be able to figure this out on your own. But that's going to be a ways down the road. Okay? So when I say carbon is in the middle, this is what I mean the structure is generally going to look like. But now here we're going to draw the whole thing starting from scratch. And we always start with the Lewis dot symbol with the correct number of valence electrons. Okay? Now, remembering our general rules, Carbon's probably going to need 4 bonds, chlorine's going to need 1 each, and oxygen's going to need 2. So keeping that in mind, let's start with the chlorines because that's easiest. They need 1 bond, so they're going to share a pair with the carbon so that each of theirs is paired up. So the chlorine's octets are now satisfied. And again, this will look really messy before we clean it up a bit. And then the carbon has 2 bonds that it still needs to make. And conveniently, the oxygen still has 2 bonds it needs to make. So these guys are going to pair up, and these guys are going to pair up. Okay? So when we clean up this structure, what it's going to look like is carbon double bonded to oxygen with 2 non-bonding pairs. Move this over even more so it's a little easier to see. And then carbon bonded to chlorine. No non-bonding pairs on carbon. You'll start to notice that as carbon never has, not never, very, 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 very rarely has any non-bonding pairs. It just always has 4 bonds and no lone pairs or non-bonding pairs. If you look at nitrogen, that's typically how nitrogen's going to look, is 3 bonds and 1 lone pair. Or oxygen, 2 bonds and 2 lone pairs. Or fluorine, 1 bond and 3 lone pairs. That's how it, those bonds adds up to the number of lone pairs. We could even put this up here. This is something that you can kind of understand on your own, but I'm going to put it up here just to emphasize it. The number of lone pairs or non-bonding pairs, they have to add up to a total of 4 pairs, right? So you're basically just taking 4 minus the number of bonds. So for this one, you're going to have no non-bonding pairs. For nitrogen, you're going to have 1. For oxygen, you're going to have 2. And then for the halogen group, you're going to have 3. Remember, this applies to everything in that group, not just the elements that we're showing. We're just using those as examples. Okay? Okay, so coming back to our structure here, chlorine is going to have its 3 non-bonding pairs and its bond. So this is our final structure for CCl2O. Okay? A little more complicated, but I wouldn't say hard, right? All right, next one, it says all 4 atoms are in a row. The carbons have to be in the middle of that row because hydrogen, remember, comes in with 1 electron and then it needs to share. So it'll form a bond with something else, but it's only ever a bond. It's never a lone pair on anything on hydrogen. And hydrogen could never form a second bond. So because of that, we mean that hydrogen has to be on the outside, just forming a single bond with something else. This is because of that duet rule, or the fact that hydrogen starts with a single electron and it only has to fill up that 1s orbital, so it doesn't need a total of 8. It just needs 2. Okay, so even if I hadn't told you, you should know that the hydrogens are going to be stuck on the outside in some way. Okay, now let's go in and draw in the, and if you want to continue to color code it to make sense for yourself, by all means do that. I'm just going to do it for the sake of time. I'm going to stick to single color from now on. Okay, so I've drawn each atom. I've drawn the correct number of valence electrons on it. So I've drawn the Lewis dot symbol, and now I'm going to pair them up. Okay, so the hydrogen's going to pair with the carbon on each side. And now all I've got to do, the only thing I can do is bond those carbons to each other. And they already have 1 bond. They typically need 4 total. And it has 3 unpaired electrons on each atom. So hopefully you've guessed that these guys are all going to pair up or create a triple bond between the carbons. and then an individual hydrogen on either end. So this would be the correct final Lewis structure for C2H2. No lone pairs because they've all been paired up. And that's it. Okay. All right. Now the last Lewis structure, the last topic that we're going to cover is quite a bit different. But it's an important thing for us to discuss as we're doing these Lewis structures. So the concept is electronegativity. Now, trying to think, depending on the class you're in, you may have hit electron affinity, but for a lot of you, this is going to be the beginning of discussing this topic. What we did talk about at the end of Chem 1 was ionization energy, which if you remember, ionization energy was the energy to remove an electron. This is kind of the opposite of that. This is the ability to attract an electron. Now, we have this funny, I had a professor that called it this one time many, many years ago, and so I've kind of stuck with it. The other thing he used to call it is the electron sucking power. It's kind of silly, but when you think of it like this, what I start to call it is strength of the atom to attract the electrons. So it kind of all fits together. So when you think of it as like its ability to suck the electrons close to it, that kind of makes it seem like if something has a higher electronegativity, it's going to be stronger. Okay. So if you look at this chart, you can see that the atoms over here have the highest electronegativity. So we actually assign values to this just to give us a sense of how they change. So if you can see, fluorine is 4.0. And then it steps down by 0.5 as you go, back from right to left from fluorine. So 3.5 for oxygen, 3 for nitrogen, 2.5 for carbon. Okay. As you go down, the jump is a little bit more dramatic initially. So as we go from fluorine to oxygen, let me just zoom in, that might help. As we go from fluorine to oxygen, it only drops 0.5. As we go from fluorine to chlorine, it drops to 3. Okay, so that jump down a column is more dramatic initially than going across a row. But if you also notice, as we go across a row this way, now those jumps begin to get a little more what they were like above. They're actually a little bit less dramatic once we get to the lower rows. So you're not going to have to memorize these. There's a chart in your exam equation sheet that has the actual numbers, but just being familiar with them. And I think this visual representation is really useful. The other thing that's really important that you connect it with is that, let me put that circle back, that we said this section has higher electronegativity or ability to attract electrons. And a really key point to remember from chapter 9 is that these are also the smallest atoms. Okay, so the smallest atoms are the ones that have the highest electronegativity. So just think about for a second why that might be. Why would a smaller thing be able to attract the electron more? Okay, so it says think about the potential energy of the electron as it relates to how close it is to the nucleus. So if I've got an electron that's able to come this close to the nucleus versus a bigger atom where it's going to be this close, the electron is definitely going to want to be at that lower potential energy. Everything tends towards a lower potential energy. And in atoms, electrons, and nuclei, the closer they are together, the lower the potential energy. So when you have a small atom where the electron can get very, very close to the nucleus, that's why it has a great ability or a great electronegativity, a great ability to attract the electrons, because those electrons can get very, very close to the nucleus when the atom is small. Okay, so that's the idea behind electronegativity and kind of its connection to size. You'll also notice it's related to ionization energy. The things up here that are really good at attracting electrons, they have really low ionization energies because they don't want to give those electrons up. So the electrons are very difficult to be removed. So they have high ionization energies, but very good at attracting additional electrons. Okay, so we're going to go ahead and work through this chart. I would like you to pause at this point. If you had any problems with the Lewis structures above, really I should have had you guys pausing at each one of those and working them on your own. Certainly at this one, let's go ahead and do that, okay? All right, so it says calculate the difference in electronegativity. So difference meaning, let's compare the two and subtract them basically. So KBR, we're going to look at our chart. And if it's easier for you to look at the exam equation sheet, those are written a little more neatly. So K is over here. And BR is over here, 2.8. Okay. So 2.8 and 0.8, you can do that in your head pretty quick, but 0.8 and 2.8, or a difference of 2. Okay. HBR, H is 2.1. I know that one off the top of my head because it's one we use frequently. And BR is 2.8. So the difference is 0.7. Okay. And then BR2, well, both of those are 2.8, right? So the difference is 0. What we're going to do is we're going to define the type of bond that exists. And by this, I mean, it's going to be in a picture in the next one. So I'll scroll down there in a second. But we're going to define the type of bond. In general, we're talking covalent versus ionic by the difference in electronegativity. Okay. So when we look at this chart down here, there are actually values for what the difference in electronegativity is and how we're going to decide the type of bond that it is. Now, this should feel weird because before we just said ionics are a metal and a nonmetal. Well, the reason why that's the case, why when you put a metal and a nonmetal together, the electron actually gets transferred from one to the other. Let me rewrite this because the picture that's shown here is actually nonmetal on this side and metal over here. So the electron actually gets transferred from the metal to the nonmetal. The reason why that happens when we have a nonmetal and a metal is because there's a very big difference in electronegativity. Okay, so when we put the two atoms together, one of them is very, very good at attracting electrons, the nonmetal, and one of them is, well, really bad at attracting electrons, or another way of saying that is it has a low ionization energy. It's really easy to remove electrons from it. So if you pair something that has a high electronegativity, so I'm going to use our, let's see, do I have an example right there? I'll use the example we used before. So that was KBR. So we'll pretend that this is BR and that this is K. This was 2.8 and this was 0.8. So when you have a big difference in electronegativity, and the way we're going to define big is a difference of 2 or higher. When you have a big difference in electronegativity, that is when the nonmetal is so strong or is so good at attracting the electrons that it just rips it off of the metal. Like, it's not even just that it attracts it well, it attracts it so strongly that it rips it from the metal and creates an ionic bond. Okay? On the other side, the pure covalent bond, or what we call nonpolar, we'll get to that in a second, is ones where the electrons are shared exactly equally. Okay, so our example above was bromine, Br and Br. We said that had a value of 2.8 and 2.8. So think of this like a tug of war where the two atoms are equally strong. All right, if they're equally strong, no one's going to get more of the rope than the other person, right? They're going to share that rope equally. So when we look at the Br2 element, or sorry, molecule, they share the electrons equally, and so nothing happens. It's just kind of, we would think of it as a neutral molecule. This will make a little bit more sense when we get to the next example as well. Okay, so that's when the difference is 0. We actually define it as really small differences. We'll call those nonpolar, or how they're sharing the electron equally. So it's written right here. So anything less 0.4 or less, so we'll say less than or equal to 0.4. Okay. Anything in that range, we're going to consider it to be nonpolar. So an example of this would be like C and H. H is 2.1, C is 2.5. So they are different, but the difference is so small that it's negligible. It doesn't really matter. Okay? Well, what about this middle region in here? So this would be the example that we had of H and Br. So 2.1 and 2.8. Okay, so the difference here of 0.9, let's see, was that the, 0.7. I just did the math wrong. So 0.7 is the difference here. So it lays in the middle between this 0.4 and 2.0. And what it's really telling us is that the bromine is strong compared to the hydrogen. It is better at attracting the electrons than the hydrogen is, but not so great that it's going to rip the electron away. So again, think of the tug of war. Think of there being like a rope in between. The electrons in the bond are like a rope in between the two atoms, but the bromine is strong enough that it's tugging on that rope better, and it actually gets some of the rope to go further over to its side. The hydrogen can still hold on to some of it, but the bromine is pulling on that rope and getting more of the rope. Okay, so when that happens, what we're saying is that the electrons that are in this bond, so instead of drawing it as just a line, I'm going to draw it as a rectangle. So over here, those electrons are equally divided amongst the two atoms. Over here, the electrons end up spending more of their time over by the bromine. So I'm trying to represent that in the bond by showing that these two electrons are not evenly distributed between the two atoms. They're spending more of their time over by the bromine. Whereas in the ionic bond, the electron has completely moved over to the bromine. Okay. It's actually the two electrons, the one that it came with and then the one from the potassium. Okay, so those kind of, you can think of them as they were a bond, but then it got completely pulled away from the potassium. Okay, so what does that do to the molecule itself? When those electrons spend more time over by the bromine, okay, so we're over here on this HBr one. It's hard when I can't point at the screen to show you. But when the electrons spend more time over here by the bromine, what happens is that the molecule develops a slight charge on the side where the more electronegative atom is. Let me just write that down. So molecule develops a slight charge, and by charge I just mean like positive or negative, on, I should specify, on each side, we'll say positive on less electronegative side or less electronegative atom, negative on more electronegative atom. Abbreviate that. Okay. So we mean that because the electrons don't get divided equally amongst the bromine and the hydrogen, they spend more of their time over by the bromine, we will actually see a slight charge on this side of the molecule because the electrons are over there more and electrons are negatively charged, okay? And on the other side of the molecule, we see a slight positive because the electrons are spending less of their time over there. And so there's slightly less negative charge than there was originally. We don't see that when they attract the electrons the same. When we look at a pure covalent or a non-polar covalent bond, they share the electrons equally, so there's no charge on the molecule itself. Then when you go to ionic, this is something we've known already, but now it makes a lot more sense. The electrons don't just spend more time over by the bromine, they just move and spend all their time over by the bromine. So they get this full negative charge. Let me erase some of this circling and starring and whatever before we continue. Okay, so when we showed these symbols, this it's like an incomplete figure 8. It's the Greek letter delta, lowercase, but it means partial. So this symbol here means partial negative, or like it's a little bit negative. When we look at the ionic bond, it's a full negative charge. We would say minus or like -1. The 1 is implied there, meaning the electron has fully moved over to this side. With this one, we're not saying it's -1. It's like maybe it's minus, we're not going to give these numbers, but maybe it's like -0.2, or maybe it's -0.4, or maybe even 0.6, but it's not a full -1 charge. So we use that symbol to say it's partially negative. Okay, so again, recapping, when there is no difference in electronegativity or a very slight difference, we call that non-polar or pure covalent. And this happens when either the atoms are identical, like bromine and bromine, or if there's only a very slight difference, like carbon and hydrogen. An ionic bond, well, let's go ahead and go with polar covalent. A polar covalent bond has partial charges because the difference in electronegativity is significant but not enormous. So somewhere between 0.4 and 1.9. And what we mean is that the electrons are spending more time by the more electronegative atom, and so that develops a partial negative charge on that side of the molecule. We call it polar because if you think of like North Pole and South Pole, those are magnetic differences, and this is electron or electromagnetic differences. It's not the exact same thing. But you can kind of think of it like the poles of a magnet, okay? So they're charges on the side of this molecule. And then if we go all the way over to ionic bonds, that's where we have a difference that's greater than 2. And that's where the electron moves completely from one to the other and creates a full negative side and a full positive side. So it still does kind of have sides of the molecule. It's just that it's completely negative and completely positive. Okay? All right, so one last thing we want to talk about before we're done. Hope we're not too far over on time. But we want to talk about what happens when these these molecules interact with something else that's polar. Okay? So water is the most common polar molecule that we see. So let's draw water maybe on this next page where we have a blank. So water is H2O. Oxygen starts like this. Then we bring in the hydrogens. And they form a bond. Okay? A lot of the times you'll see me draw water like this, kind of at an angle instead. And the reason I do that is because this side of the molecule where the oxygen is, first of all, let's look at the electronegativities. Oxygen is 3.5. Whoa, didn't mean to do that. Let's see. Sorry if you can hear the TV in the background. I'm forcing my kids to run on the treadmill before they start their Zoom school. And they've got the TV up nice and high. Okay, so the oxygen is 3.5 for its electronegativity, and the hydrogens are only 2.1. So there's a pretty significant difference in electronegativity there, okay? So let's see, 2.4, the difference in electronegativity. Nope, sorry, 1.4. I was like, that is not right. So there's a pretty significant difference. Oxygen is very electronegative by comparison, and so it will attract the electrons towards it and create a partial negative charge. Put that in red just to emphasize it. This side of the molecule will have a partial negative charge, and the water will have a partial positive charge. Okay? So what I want you to think of is every time I draw a water molecule, I want you to imagine that the oxygen side is negatively charged, almost like, the chlorine would be in NaCl. Okay? It has a slight negative charge. And what do we know about positives and negatives? They attract each other. Okay? So let's look at this first one here, KBr and H2O. Now, if I have KBr and it's a positive and a negative, okay, and then I bring water in here, which has a negative side, which thing is going to be attracted to that negative side? Well, positive and negative attract. So the potassium is going to be attracted to the negative side. Water also has its positive side. It's bugging me. I got to color code those better because it's confusing. So this is the negative side of water. This is the positive side of water. Water also has its positive side. So where do you think that bromine is going to go? It's going to go be attracted to the positive side of the water molecule. So when we're looking at this, when we see the interaction of an ionic compound that has a full positive and a full negative with water, those two ions will actually separate and they will interact with the water molecules. It's in a very specific way that we talked about, I think, in chapter 5, where we talked about solutions. So potassium gets surrounded by the water. I'm not going to draw the lone pairs on here just to save time. And all of the oxygens point towards the potassium ion. So we talked about this in that chapter, but you guys now have a much better understanding of why that happens. Because all of those oxygens are like the negative side of the water molecule. And so they get attracted to the potassium because it's positive. Then we look at the bromine and all of the water molecules get attracted to the bromine, but it's the hydrogen side that gets attracted to the bromine. Okay, and this is what ionic compounds look like in water. Their ions separate. The negative ones get surrounded by the water with the hydrogens pointing in. The positive ones get surrounded by the water with the oxygens pointing in. Okay, what about something like HBr that doesn't separate into individual ions, but it does have sides to the molecule? So if we've got HBr, and like we said in the previous page, this is partially negative and this is partially positive. And we bring water along that we know has a partial negative and partial positive side. What do you think is going to happen when these guys interact? Let's see if I can rotate it with, I'm not sure if I can do that. Oh, yeah, I can. The molecule is going to rotate itself and like orient itself so that its positive side is pointing towards the negative side. And guess what? If there's a molecule, another HBr molecule over here, it's going to orient itself so that its negative side is attracted to the positive side of the water. Okay, so things start to kind of line up, and it hugely affects how things will interact in water. Now, if we have bromine that has no difference in charge because there's no difference in electronegativity, it's completely neutral, When we add water in there with these partial charges, there's no preference now for how bromine does or doesn't get attracted to water. In fact, it probably wouldn't be very attracted to water at all because there's just no motivation there. There's no charge to pull it in. They're not going to bond because they already have their octet satisfied, but there's also no charge to attract them. And this is at the heart of the whole idea of like dissolves like, if you remember from chapter 5. Things that are polar, like HBr, will dissolve in other things that are polar, like water. Something that is non-polar will not dissolve in something that is polar. So these guys probably won't even mix. Okay? All right, so then on Wednesday, when we come in, please make sure that you've done a decent amount of the chapter 10 homework. There's no reason why you can't have like almost completed it because we're about 3/4 of the way through the chapter. So when you come in on Wednesday, we're going to do some more complicated molecules, and then we're going to apply this idea of polar bonds to now molecules and say, well, what happens when there's multiple polar bonds in a molecule itself? Okay? All right, stay safe. Do plenty of studying, read up on the things you need to. Feel free to post comments in the YouTube for questions. And then, like I said, do some of the homework to kind of prove to yourself, do I understand this well enough to do some of these problems on my own?